All right, folks, welcome back. Now we are going to go into one type of autoencoder that is very powerful and, in fact, the first very effective generative model that we are introducing in this course. Right? From here onwards, just about every architecture we'll do in the next few weeks will be generative in nature. Are we together? So let's talk about variational autoencoder and what it is. There is quite a variational autoencoder, actually, many people argue, has very little to do with autoencoders. Like if you come from a Bayesian inference theory, so there's a subject called Bayesian inference. And if you come from that world, you would say, some people even scoff and say, this is all Bayesian theory. The fact that it's in the form of an autoencoder happens to be an accident. Right? Then if you come from the world of, you look at it from the lens of autoencoders, you think of it as a very good and neat way of resolving some of the issues that the traditional autoencoders have. Right? So just be aware that when you encounter literature, you will encounter, you'll encounter this variation, well, I shouldn't say variation for variational autoencoders, but let's say the spectrum of perspectives when they talk about this topic of. So what is this? Let's talk about variational autoencoder. So I'll give you a very baby version of something called a whole theory that is called variational, well, not baby version, there's just a simplified version. So variational, am I writing it right? Am I spelling? Variational inference. Variational inference is something quite interesting. Let us say, I'll give you an example, a very practical example. Let us say that you have, I don't know how best to say it, so I'm trying to cook up an example on the spot. Suppose you have a pan of water. Right? So today morning, you decided it's a great time to make tea. Right? So you take water and you start feeding it some heat energy, and which you control with your stove has some dial, and the dial is pointing to this or this or this. You know, how strong of a heat is that? What you guys have, rotary dials to control the heat going into the amount of heat going into the pan. Now, let's say that the observed effect is steam coming out, steam volume. Are we together? Right? That could be an observed effect. So this is the observable, observed. What is not observed is the cause of that steam coming out, which is the supply of heat to the water, to the pan of water. And the more heat you supply, the more steam comes out. Are we making sense, guys? So you say that Z, which is heat, intensity, is causing X, which is steam, volume, right? The steam volume flow. Does that make sense, guys? How fast, how much steam is coming out, the rate of steam or steam rate is actually there. But suppose you couldn't see the knob, you couldn't see this, you would still argue that, hey, I should be able to infer from the observed, I should be able to create a model of, I should be able to infer exactly where the dial is set on the stove. Does that make sense, guys? By looking at how much steam is coming out and how it is varying, I should be able to tell it, right? So let's say that given this heat, there is a function Fz, x is equal to fg, but I should be able to invert it and infer what z produced this x. Know the reverse function, right? Essentially, figure that out. Isn't it very intuitive when you're boiling water, when you're making tea? So to do that, to go from the observed to the latent. So what we say is that z is your latent variable because I've hidden the dial from you. You can't see the dial. What you can only see is the amount of steam coming out. But you have to infer the latent variable, the hidden thing, exactly what was the dial setting, which we have hidden from you, let's say. So to be able to infer z, the latent, from the observed is inference. That is the meaning of the word inference. Are we together? And there's a whole theory of coming up with these inference, which is goes back to a mathematician called Bayes, right? And it's called Bayesian. Well, he did something very basic, but people built upon it. Bayesian inference.
Asif, how is it different from causation?
No, see, causality is a little bit of a stronger statement. It's a close cousin. If you say that Z is the only cause of X, as in this particular case, then yes, causation. But if Z is one of the latent factors, then you just say that X does depend on Z. Right? There may be other factors also, other latent variables also there, other things also there. But you can, roughly speaking, you can think of it as causality. But I mean, see, there is a whole mathematics of causal inferences and so on and so forth, which I won't go into at this particular moment. But just look at it like this. Leave it as a Bayesian inference. But very close cousin. Let's just say very, very close cousin.
So would it be correct to say another example of this heat intensity? If you're watching the car go fast and it's trying to predict what is the speed at which the car is moving, is that?
Yeah, one thing you can do, yes. So Bhavin is giving the example that car is going by observing how much time it took to go from A to B. You can infer what speed it was going at. That itself is, yes, it is inference because the speed is the latent there, right? Or much more appropriately, by counting the number of tickets you got as a youngster, one can infer how fast you were in the habit of driving. Right? That is Bayesian inference, simply put. So I hope we got the idea of Bayesian inference. Right? Now, why is that relevant? It turns out that some of the mathematics that we'll use, which by the way, I just thought of a way to avoid all that mathematics altogether. But the reason I'm mentioning it to you is because you should know that you have entered deeper waters. And in this, there are all these creatures swimming, and they have the word Bayesian attached to it. And there is also something called elbow, right? And elbow stands for expectation lower bound. And there is one more concept which stands there, which is called KL divergence. It so turns out that I'll teach you KL divergence because it's worth knowing, right? But I'll keep to the simplest one, just the KL divergence. But we have entered a little bit deeper mathematical waters. But before I go into that, let me give you the main intuition of why we are going into that. Let me give you the big picture first. All right, guys? See, the problem that we have with autoencoders is this. If you go back and look at the way, for example, this is the Z space. You have inputs, let's say inputs were your MNIST digits or whatever it is, right? When they got projected, if you observe how they got projected into the latent space, you would notice that they would show a peculiar spread. Let's say some things would be here, some things would be overlapping and be scattered around here, and something else would be, let's say, scattered around here. Now, when you look at this, and there is a lot of overlap here, so there are regions in which it is hard to tell which of the digits, for example, it could be, or if you're looking at animals, right, what it could be, right? Or let's say that you're cooking food, right? And you have a dish. Let's say you have rice. And let's say that you have sambar soup, some soup there, right? Now, one of the things is, some of the things that are desirable, remember what I said is, suppose the latent vector for Z and the latent vector for soup are here and here. Wouldn't it be nice if by going from here to here, I could, picking points along this journey, I could tell how much rice you have put into the soup? Does that look like common sense? Right? It would have been nice to do that, right? So suppose I pick this point here, A, then I'm mostly rice and a little bit of soup. If I'm here, then I'm mostly soup and rice is barely visible. It would have been nice if we could do that. Yeah. But the problem you have here is, it's very hard actually to do that kind of journeys in a typical autoencoder space, because a point here where I'm putting the cross there will become indecipherable. Machine has no way of understanding what it is. It will just produce a random figure, or not a very meaningful figure. Are we together? Right? It knows how to do things here. It knows how to do things here. It knows how to do things here. And then there's a big region of confusion in between. Right? So there's a problem here. So you can't do generative models. You see that? The quality that it is missing is a generative ability. I can't train it and create arbitrary mix of soup and rice, sambar and rice. Am I making sense? Right? So I cannot have a bowl of rice, or let's say they are potatoes. Right? Well, the moment it's rice and potatoes, usually most men lit up. Yes. So how much of potatoes are got with broccoli we put? So imagine that here is broccoli, here is rice, right? And here are potatoes. I should be able to pick a point, and let's say that in the data point, I've only shown it broccolis and rice and potatoes, but possibly not many pictures of them all being in the same plate, right? And yet it would be nice if it could do that overlap, right? Add some potatoes to the rice and so on and so forth. So that kind of generative ability, it doesn't seem to have. Or very practically speaking, when you do facial generation, right? Or people play this game. How would you look when you were young? How would you look when you're 20 years older than you are today? And how would you look if you're 10, 20 years younger than you are today? Right? So the younger part is actually very practically useful. What people do is they will generate a younger version of themselves and then promptly put it on social media. This is how I look. Right? So you could do that. Or, how would I look with a beard? Different sizes of beard, different kinds of mustache, and so on and so forth. So you can, how would I look without glasses, and how would I look with glasses? But you can't do that kind of gradual progression as a generative activity. And it just boils down to the fact that in the latent space, there are sort of holes in there. You see these black holes, these regions over which the machine has no idea what to do, what it is, because none of the training data, it's stored there. latents, whenever it produced the latents, it had nothing in those spaces, no latents in those spaces. So if you give it a latent from that space, if you sample from that space, it has no way to decode it into something sensible. Are we making sense, guys? Right. So that's the main problem. So here is something you could do. What is the desirable that you're shooting for? The desirable that you're shooting for, and I hope you pay attention to this, because at the end of it, all of math boils down to some simple statements. And I'm making a statement that captures a bucket load of mathematics here, right? Hard mathematics usually. So what we are saying is, what if two things were true? If all the points were around the origin, let us say, right? They were all like this. And let us say that there was a region. This is the region for something, let's say rice. This is the region for potatoes. This is the region for, let's say, soup. This is the region for, I'm just making up examples, right? This is a region for broccoli, God forbid. Right? And now, do you realize that if it is true, what does it mean? If it was all tightly near the origin and there were no holes in the space, you realize that I can, even though the real data on which this machine was trained led to this latent representation, I can just sample from the latent space close to the origin, pick any one point, and I know it will become something sensible, right? If it were faces, I can just sample into this and produce an infinite variety of human faces. Are we together? And therefore, you will see that people, and this is one generative model, GANs, and we'll learn many other generative models. Their entire websites devoted to things like this person does not exist.com or something like that. Right? They all use generative models. This is the first one you're learning, but they all ultimately are based on the fact that there is a latent representation, right, into which you can do vector arithmetic, right? You know that this is the place with guys with mustaches, and this is the place with clean-shaven guys, and I can gradually grow a certain degree of mustache on a face, get a guy with half a mustache or just a hint of a mustache, and so forth, by interpolating between the regions, between the latent space. Are we together, guys? Right? Not only that, it becomes a generative model. So pay attention, guys. You realize that we talk of generative AI, but at the end of it, that big mysterious word comes down to something very simple mathematical ideas. You realize if I could have a tight latent space in which every point within proximal to the origin I knew was sensible point, that it could be decoded into something realistic. How many points are close to the origin? Suppose I take just a unit circle. Let me just take a certain radius of a circle. How many points are close to the origin? Infinite number of points. And because there are infinite number of points, what does it mean? I can produce an infinite variety by sampling off the space, latent space. Just jump somewhere in the latent, just throw a dart somewhere in the latent space close to the origin, right? And decode it, pass it through the decoder part, right? Pick this Z. So Z sampled off this zone, sample a point of this. By the way, this tilde symbol, whenever you see me use, you see this weird symbol? Yeah. It in our language, in machine learning, it is this, what we are trying to say is sample from, or randomly pick from, if you want to use the more colloquial word, randomly pick from. Let's say from this particular disk zone, right? Origin, around the origin. And then Z, that random point that you pick, pass it through the decoder, and what will come out? Suppose it was a face, it will come out like a realistic face. Making sense, guys? Right? Or if it was food, it will look like good food, right?
This might be a stupid question. The infinite number of points, try to understand the intuition of it. I mean, one way I think is like you can keep slicing that space, says between 0 and 1, and can keep slicing into smaller chunks. You can continue to do that until the practice of physics, but I wonder if there is I'm completely wrong.
Yeah, see, think about it this way. Theoretically, it's infinite because between any 2 points, they're still infinite number. So if you take 0 and 1, we say how many points there are. You can say, well, there is 0.1, 0.2, 0.3, all the way to 0.91, let's say. But then between 0 and 0.1, again, there are infinite number of points. 0.01, 0.02, you see that. But between any of these 2 points, again, there are infinite number of points, right? So you can keep, there is no end to this. Between any 2 points, there are infinite number of points.
So in the mathematical term, there is no end to it.
There is no end to it. That's why the symbol infinity is this.
But if it's a physics, from the physics standpoint, you will reach the atom where you can't break the atom further.
Oh yeah, I mean, see, one has to understand it conceptually. In terms of physical notation, you could attach the atom. Atom comes from the Greek word atomos, indivisible, except that atoms are not indivisible. You can break them up into subatomic particles, the electrons, protons, neutrons, right? We know that. Even those are not indivisible. They are made up of, we hypothesize, quarks and gluons, right? That's, for example, that's what I was doing my doctoral studies on. Are they fundamental? No. The hypothesis is that they are made out of strings. Now, are the strings fundamental? No. We know that they are effective theories, but we don't know what they are made up of. Right? So it can keep going on. The logical way to think about it is that as an intellectual journey, as a Gedanken experiment, thought experiment, you can keep zooming in indefinitely. Now, in practical computer science sense, there is a real limitation. Suppose you're counting numbers as floating point FP32, 4-byte floating point. Then, of course, there is almost only that much resolution you can have. Right? In fact, that is a resolution that astronomers met. Right? People who are in physics, they often hit the limit. That is why, for example, in languages like Java, they don't use the normal float or double. They actually have something called big decimal, whose resolution is way bigger and higher, because their range in physics, the range is almost from 10 to the minus 32 or minus 40, all the way up to like unimaginable numbers, the radius of the diameter of the universe, right? So if somebody says, oh, it took a million years for the light to come from there to here, we say only, oh, that's pretty close, right? That's how astronomers think. But think how fast light travels, and you'll realize what it is, what astronomical distances we talk about. I used to think astronomical distances are big, but somebody once quipped and said, well, economic numbers are bigger. Have you looked at the national debt? So no arguments there. Anyway, so that's that. Getting back to it, guys, the point is that if you can create a rich latent space, right, which has no holes in it, meaningless holes in it, then you can sample off that latent space and create a near infinite variety of things, faces, and that is generative. And thus a generative model, the first example of a generative algorithm.
So how these walls are getting filled?
That's the question. Would you like to go on that mathematical journey? Okay, let's go there.
So just before going,
Yeah.
Yeah.
We go to the previous diagram, which one shared. So to that to here, I mean the sample distribution is a little bit out of the origin, and here we are saying that within the origin. But
Oh,
here
no,
also-
no, that is not. It was around the origin. This line
that
I
was
could have
also-
put. Yeah. That is just because I was being sloppy. So yeah, if it helps you, I'll put it there. It has
This
nothing to do.
space as well, where we have a space of confusion as like what we showed around here also. So
Right.
when we are trying to zoom into the infinite, where we are reducing, since we have so many infinite points, we are trying to reduce it to a sample size.
Yeah.
I'm not able to map it out. Still, it's a gray area, right? How is it able to figure it
Yeah.
out?
What, see, the problem is, so first of all, and I'm going there. So
Okay.
in a way, I'm getting there. So guys, let me summarize. The problems with the traditional autoencoder, the vanilla autoencoder is, first, it distributes the point whichever way it finds efficient to be able to tell or to be able to reconstruct those things, the training data. To do that, it might spread them around. The other thing is, all the digits, let's say eights may not be in one place. Some of the eights are here, and some of the eights, for example, may be here completely. It may just have disjoint partitions in the latent space for the same time. And so there are all of these pathologies that people just frown upon. So what do we do? What do we want to do? We want the distribution to look like this. Right? Now, what is this distribution? What are we saying? Very much close. Most points should be close to the origin. Right? Now, when people say very close to the origin, usually there is a way to say that. Does anybody know? If I want, let's say that I want most. If you look at, for example, most adults' height, what would the height look like? Would it look like this, a bell curve? Right? Most adults are, what is it? 5'8" plus minus something. Does that look reasonable for men? And maybe 5'6" plus minus epsilon for women, or something like that. I don't know what the actual numbers are, but does that look reasonable? Oh, by the way, I hope I don't come across as sexist for saying women are any the less in height. Okay. Let's reverse it just to be safe.
You can do life expectancy, even have more higher life.
Oh yes, that's a better life expectancy. Let's go with life expectancy. Yeah. So yeah. Right. So all right. Given that, so what are we saying? We want most values, a bell curve. This is what do we call this? A bell curve, right? So the most common, the most intuitive notion of a distribution of data in which we say most of the values we want close to a certain thing is a bell curve, isn't it? What does a bell curve have? Just to give you a refresher on a bell curve, it has an origin. Usually you can take it as 0, for example. In our particular case, we can take it as 0 if you wanted to, right? But some mean, it has some mean, and it has certain amount of spread. So for example, this curve is blue is more spread out than the yellow one, isn't it? And the purple one is much more spread out than either of the two, or the other two. So the spread is measured by variance or standard deviation. Right? When you square the standard deviation, it's variance. Actually, in field like in basic high school statistics, you're mostly taught about standard deviation. But in machine learning, we don't use the word STD so much. We just use the word variance because it's just easier to compute. Like you just forget about taking the square root. So you speak of sigma square, the variance. Right? So in other words, a bell curve is given by mu sigma squared, these two properties. Would you agree that any bell curve, and it is represented by this notation, any bell curve is parametrized by a mean and sigma square, and you can find a point in the bell curve. Now, generalize the bell curve. So one way is that you take a bell curve and spin it on its axis. What will it become? a bell hill, isn't it? It will become something like this. But this bell hill is sort of symmetrical. It will be a nice one because you just spun it. And now you stretch it a little bit. In one direction, it's a little bit more spread out. In other direction, it's not so spread out. So you would agree that if I take a bell hill, it's first is that in a plane, let's say x1, x2 plane, there will be some place where the center of it will be, of the bell hill will be. And that, let me call it the mu vector. It will have a mu1 and a mu2 component. Do we agree, guys? Center would be given by mu1, mu2. And also, and here comes the part that it will have a certain spread. Right? If I project it along the first axis, like you look at the shadow of that bell hill on the wall, one wall along one axis, you will what will you see? You will the silhouette will be a bell curve, isn't it? So because the silhouette will be a bell curve, that will have a certain sigma 1 square along, let's say that you look against the x1 wall. Likewise, if you look at it along the x2 wall, the shadow of it, it will have square, isn't it? And then if you, but then that's not enough. What if you look along a different axis wall, in between axis wall, right? So there will be there is a potential for cross engagement. In other words, your bell curve may be not, it may be sort of deformed, slightly deformed, right? And so it may have some other terms. Let me call it 1, 2, 1, 2. So there's you can convince yourself that even if you take like this and like this, but you can still, in this other direction, you can still fool around with it without these values getting affected. Right? So this thing is a generalization of standard of variance, right? So you can say that in a two-dimensional space, it is given by this mu sigma, this big, this is the big Greek letter for sigma. Right? It is given by this. Are we together, guys? This matrix. Right? See, if it just helps you to think in the beginning, just think that sigma is just, you realize that one shadow along one wall will produce this sigma square, another shadow along another wall will produce this. If it helps you in the beginning, right, just assume that these terms are zero. Then after a little while, you can generalize from there. Right? Now, this is in 2 dimensions. What happens when we go to 3 dimensions? Right? Or n dimensions, mu would just become mu1 all the way to mu n, isn't it? As you can clearly visualize, right?
Yeah.
Okay. And likewise for sigma. Yeah. The variances, there would be variance against each of the walls in the n dimensions. Right? So you could have. So, but the main point is that you can represent a bell curve's generalization. The word that people use is named after a mathematician, Gauss, right? Gaussian distribution, Gaussian distribution. You want your latent space, for example, if it showed a Gaussian distribution, what would it mean? That in the n-dimensional space or d-dimensional, so Z, let us say Z belongs to d-dimensional space. In the d-dimensional space, most of the points are clustered at one place, isn't it? Probably close to the origin, they're just clustered there, and then they gradually diffuse out, and they pretty much vanish. They thin out. Far-off points actually don't have much relevance. So that's a Gaussian distribution. Why is it called Gaussian distribution?
Because
Oh yeah, because Gauss wrote the equation for that. And it is the celebrated equation, e to the minus x minus. So in one dimension, it is x minus mu over sigma square, a half of it. Now, this looks like weird, isn't it? So guys, whenever, and then there is 1 over 2 pi, 2 pi sigma, and sigma squared. Let me just put it under the square root 2 pi sigma squared. This looks scary, right? And I want to use this example, y is equal to, suppose you have this. It's called the Gaussian function or Gaussian distribution. Now, whenever you see like this, does it make you think, oh gosh, where did this come from? Right? Bell curve is so intuitive, and this equation is anything but intuitive. How many of you feel like that? And let's unpack it. So one thing I want to say, guys, that actually math, nothing is actually not, everything is obvious if you know how to look at it. So should we do that little exercise? Right? So think about it this way, guys. Let's look at this guy first. What is this guy? X minus mu over sigma. Do you remember that we z valued it? From everything, if I subtract the mean, then I'm just looking at deviations from the mean. Right? What is x minus mu of any data point? It is the how either on the plus side or the negative side of the mean it is. But because data can have a spread, when I divide it by the standard deviation, what do I get? I normalize it. If you remember, in statistics, you call it the z value or normalizing of the data, isn't it? Why? So why would you normalize the data? Let's look at it. Suppose you are measuring elephants. And, you know, there is the metric system and the pound, and then the imperial system, right? If the Americans are measuring it, it has to be in pounds. If the Europeans are measuring it, it has to be in kilograms, right? So, and let's say if the Lilliputians are measuring it, it has to be in grams. It's a very small unit. But you would agree that if I want to get a sense of how much bigger is Dumbo the elephant or smaller Dumbo the elephant is relative to the standard elephant, how would I get that? You realize that that statement is invariant of what units you use. Suppose I want to say, well, relative to it, it's much smaller or somewhat smaller. I could make those statements without necessarily being unit dependent, isn't it? But how can I do that? See, while looking at the deviation from the mean and dividing it by the standard deviation, what is the unit of the numerator? Whatever unit it is, right? Let's say kg, kilogram, and over standard deviation will also be under kg. And so zi will be dimensionless, right? Does that make sense, guys?
Yes.
And so we don't have to worry about in which whether you followed the imperial system or whether you followed the metric system, right? Standard units, or the Lilliputians measure, it would still give you the same answer, isn't it? And you will notice that most data, they show a distribution such that values go up to +3 and -3. Beyond that are very, very rare outliers, right? This is 1, 2, 3. What it means is that any data that is more than 3 standard deviations from the mean, that is mu plus 3 standard deviation, it basically you can treat it as an outlier greater than this, right? Isn't it? So for example, in a normal distribution, what percentage of data points are beyond 3 standard deviations away? Anybody knows? School kids, look it up. You should know this.
What is the question?
In a normal distribution, if you assume normal distribution, what proportion of data points are beyond 3 standard deviations away? 2.5%. Well, anybody else? Yes. Yes. So less than
0.3%.
come again?
0.3%.
Yes, 0.3%, less than 1%. right? So in other words, most of the data will take on values from -3 to 3. Other than that, you'll have outliers. So anyway, so now that I put that there, you realize that y is 2 pi sigma square root e to the minus z square over 2. That's what it is, isn't it? Am I right, guys?
Yeah.
Right. Now, now let's try to. This is just a constant. Okay. Why would I need this constant? Because I want that integral of y should equal to 1. Probabilities all add up to 1, right? So if it rains or doesn't rain, the probability of it's raining and the probability of it's not raining should add up to 1, right? Or let's say that the temperature takes on values from, in California, let's say it takes on values from 30 degrees to, I think 30 was the coldest we had this year, right? 30, 32, 34? 34, let's say 34. 34 degree Fahrenheit to, this is Bay Area, so I would say the high is about 85 degrees. Let's take it that way, 34 to 85, right? So the probability that the temperature, you have a certain probability that on a given day, the temperature is whatever it is, isn't it? T is equal to, let's say 70 degrees, which is probably the highest probability. Most days we are 70 degrees, around 70 degrees here, right? So then you would agree that the sum total of all the probabilities should be 1, right? Even though it includes decimal points and so on and so forth. And therefore, it's a probability density. So this is a normalizing factor. So we can ignore it. So now that we ignored it, let's look at the rest of the equation. E to the minus z square over 2, right? Think about it this way. If I want a function that is symmetric, right? What is the easiest function I can think of that's symmetric and positive? Probabilities have to be positive, isn't it? Right? Probabilities cannot be 0. How can you make sure that no matter what the input is, the output is always positive? One of the easiest ways to do that is just take e to the x. No matter what x is, positive or negative, e to the x will always be positive, right? So you can do that. But now here's the problem. You want a function that is symmetrically distributed around, let's take the origin. Now, symmetric functions have to be even functions, remember? Even functions of x. Even functions mean, what is the easiest even function that you can think of x? Square of x, isn't it?
Yeah.
And then just to make sure that it's all very nice and positive, you could do this, right? And then you can add this to make sure that it decays and goes to 0 far off. Do you see? And this is how Gauss reasoned. And then he realized that, okay, up to the factor of 2 is just a normalizing factor, just to make sure that things add up to 1 and so on and so forth. Do you see how it is, guys? Right? And so the normal distribution is therefore given by an equation that looks like this. Easy peasy? Easy? Right? So that's the intuition behind the normal form. Anyway, that's a digression. Let's move back from the digression to our main thing. Now comes, we'll talk about a lovely topic called KL divergence. Now, what is divergence? What's it? Going away from some expectation. Right? So suppose I expected that it would be a sunny day. And then I realized that all afternoon it rained. Well, it's a divergence from what I expected it to be, isn't it? Right? So that's divergence. Now, people would say, so anyway, we'll come to that. So here is one way to think about it. See, there is and I think I talked about the likelihood function, the likelihood that something will happen, right? Which was log of probability, log of p. Right? Now, remember that. Keep this thing in your mind. Now, come back to our function. Let's look at the two scenarios. You have data that is scattered like this, weirdly scattered, the way we don't want it to be scattered. Some peculiar looking shape has arisen in the data space. I'll just deliberately make it as bad as possible, just to bring home the point. Right? Something like this. What do we want it to look like? All of it centered around this. We do want it to look somewhat like this. And let us say that we want it to look something like this as an illustration, right? So when you look at the data here, it has a certain probability distribution, right? A probability distribution P, which is given a Z, what will be the, given a X input, what is Z? Like this is a Z space, right? So where a point will land is determined by the input. As the encoder gets trained, it is determined by the encoder. So this thing means, what is the symbol stands for? Condition on the input. Given X as an input, where is Z likely to be? The value of Z likely to be? Are we together? It is that. Now, what would you, though, want this distribution to look like? Let me call this Q. You want it to look like a normal distribution. Are we making sense? We want it to look like this. Now, when you have a distribution that you want it to be, but you get something else, and what you want to do is you want to force this into this. It is called, you can first question to ask is, how do you know that these two are not similar? They are not the same. You need some way of telling that one distribution differs from another distribution. Isn't it, guys? One distribution differs from another distribution. Right? So let me go and explain this in a simple theory, but we'll leave this picture aside. I'll just give you a simplifying picture. Suppose you have a distribution that is like this. Some distribution, right? And I say, hey, this is it, but I want to approximate it with a bell curve, right? I want to impose, suppose I insist that the Q, so this is your P distribution, right? And I want to approximate it with the best bell curve that I can fit to this data. You say, well, it's not a bell curve, it's a bimodal distribution. There are two humps in it. How in the world can you call it a bell curve? You say, well, is it good enough? Just tell me what bell curve will do the job, right? Something similar we are doing here, right? We are saying, hey, I don't like it, but somehow force it to be a bell curve. Something like what's the closest bell curve we can have?
Try a bigger one on top of that.
What's that? Draw a bigger one on top of that. So what you do is, you can, first thing to do is ask, like you could start with a bell curve, simple bell curve. Let's say here, a unit bell curve. And you want to somehow move this bell curve over to have a best overlap or approximation to this, isn't it? You take a bell curve, place it somewhere, and then you drift it to have a best fit to this P. But you need to have some measure of how far apart they are, how different they are, so that you can minimize that difference, right? How much the yellow line does not look like the P line, the Q not look like P, and then we can minimize that. So one easy way we can do that is, you can say, hey, think about it this way. These are all the points along the x-axis. I can take a random point, xi, right? I know what pxi is, isn't it? The probability of xi is this guy, this point, pxi. I know what qxi is. Well, that looks depressingly small. This point, q xi. isn't it? Ideally, what would I like? That these two things match, isn't it? But they match not just here, because, for example, they do match here, but they match on average. The gap between them is as small as possible. So what happens is you look at the way to look at it is to look at for reasons that are slightly mathematical, but ignore the fact why I'm doing this. You look at the likelihood value. Likelihood value is the log of the probability. You basically want that it would be lovely if this were true. If these two were the same everywhere for whatever xi there is. But unfortunately, that's not going to happen if you look at this picture. So what can we do? We can look at the difference between the two, right? This is a measure of, in a way, the divergence between the two probabilities at the point xi. Are we true, guys? And now, if you do, with respect to all the data values, so suppose you have x is made up of x1 to xn, lots of values, right? What you can say is, okay, guys, let's look at the difference across all of them and average the difference. That could be one way of doing it. Assuming n is large, very large, sample a huge number of points along the x-axis, compute the two values, and then do this of this quantity, log pxi minus log qxi. That would make sense? Right. And now this happens to, there's a word for that. This is called the expected value of the difference, right? Expected value of sampling the data points, the inputs from x, right? Expected value of this particular difference is this, right? The average value basically is this. This is the average. Intuitively, this is on average how much the yellow line and the purple line differ from each other. Are we together? Let us say that purple is the ground truth. By the way, this makes sense, right? And this is the same as 1 over summation for I. Log p minus log q is the same as log p xi, right? Q xi. And by the way, you realize that yellow line is parameterized by mu sigma square, and the purple line, God knows what it is parameterized by. So I'll just call this phi, some parameters phi, and this is parameterized by some parameters theta. God knows what its parameters are. It's just something, some knobs that determines p and some knobs that determines yellow line, right? So for example, for the yellow line, phi is basically mu sigma square. It's a bell curve, right? So that's why in the notation, people often put this, that p is a function of its own set of parameters, internal, it's a distribution, and q is a set of all parameters. It doesn't matter. Now, because the ground truth, so the law of large numbers says, see, data is not evenly distributed. Do you notice that in reality, this data is much more likely to be here. So when you take lots of input data, most of the data are going to be clustered in this region and in this region where the probabilities are high, and less in other regions, right? So actually, it is what you're looking at is actually the weighted average of the values, right? And so in a more, and if this part you don't get, don't worry about it. This basically is that this is p xi. It is the same as probability log p theta xi q phi xi. Right. This is it. It's basically saying that I'm taking the weighted average because data, the ground truth is the reference distribution is the purple line. Points are coming from that. So this is the same as this. Just take it as a truth. And it's, and I'll just, you don't need to understand, but its continual picture is that it is a p theta xi log p theta. Sorry, in the continual, like if you look at the all points from here to there, p theta q phi x dx. Oh, that's a fancy equation, isn't it? right? This is a measure, average measure of how much this one differs from, yellow line differs from the purple line. Oh boy. But you realize that it was very intuitive to get to it. See, is this intuitive? Is this line intuitive? Yes, guys? All I'm saying is the likelihood is different. Which is this, then average of that across all points is intuitive, which is the same as, this is the same as this, or this, or this, right? They're all just variations of this. But people often write it in these, in this form actually. Now, there is a fancy name for this.
Cross interval.
No. Well, it's related to
It
cross
looks like
interval.
cross interval.
It is called, what is it called? KL divergence. KL divergence. So KL divergence, whenever you do, it's written as D KL given P. So P is the reference distribution, reference. People often call it a reference distribution, reference probability distribution. This and Q is what is trying to get close to P or look like P, right? Q is trying to get like P, and D is the measure of how unsuccessful so far Q is in imitating P. Are we together, guys? How unsuccessful Q is in imitating P, that is measured as KL divergence, right? That is this equation. That is it. Now, one thing is that this is often also called the forward KL, because you can actually have a backward KL, which is like how unsuccessful P is. Like you could do the same thing, like KL, and Q with respect to like P. Even though P is the reference, you could look at it backwards, and then the formula would be like Q log Q over P. I won't go into that. It's basically that, right? So I wouldn't go. It's basic. It's just interchange the P and Q. Now, one thing you realize that this equation is not symmetrical. Do you notice that a KL PQ is not the same as QL KL QK QP? Do you notice that the one is a P log P over Q, the other is Q log Q over P? These are widely different things. It's not symmetrical. So even though intuitively it's a notion of distance, how far apart these two distributions are from looking like each other, isn't it? But it's not symmetrical. In mathematics, we honor some measure as a distance only if it is symmetrical, positive, and positive, right? And then there's also Schwartz inequality and so forth. But the reason you use the word divergence rather than distance between probabilities is because it doesn't fulfill the concept of distance. Are we together, guys? Right? Anyway, so what has all this to do with what we are trying to do? So now what happens is, I'll give you an example. If you try to minimize the KL divergence, the forward KL divergence, what will happen is that this guy will shift itself to, I'll just tell you the final location. It will go and sit here. Actually, this is not exactly correct. It will go and sit finally like this. You can convince yourself that this is about as close as it is going to get to this. The bell curve is going to fit to the purple line.
Averaging the height.
Yeah. Okay. If you want to minimize, like this is as closely as it can mimic without changing its nature. Right? The tiger still needs to look like a tiger. The bell curve needs to look like a bell curve. Right? But it's as close as it can come to imitating the panther. Pretty much. Right? So, and you notice something very interesting. It sits upon the mean. If you look at the peak of this bell curve, it is close to the mean of the purple distribution, the average of the purple, the center of the purple distribution, isn't it? If you take the mean of the purple distribution, you'll realize that that is where this bell curve has gone and sat. Its center has gone and sat. So this is one of the things that many people don't know, that there is an intuition. It is mean sort of a seeking. When you minimize the forward KL divergence, you are making the yellow curve to be mean seeking to the reference distribution. Are we making sense? On the other hand, if you try to minimize the reverse KL, you will end up with a situation like this. You'll end up with a situation like, oh, no, I should use a different color. Where is my different color? This. Okay. You will end up with a peak that is like green. What is green doing? It is mode seeking. So if you try to minimize the reverse of the KL divergence, right, it will go and sit at what point? So look at the green. What is it picking up in the reference distribution?
Most number of offenses. Yeah,
the peak of it. Where is the peak of that? The tallest peak in that distribution. It will go sit there. It is anyway, this is a huge digression I made on KL divergence. It is perhaps unnecessary, but I did that because we'll encounter KL divergence throughout our machine AI journey as we do many things. It is one of the most common metrics or one of the most common tools that we use and often used in the loss function. So now come back to it. Now the rest of the journey should be pretty easy. Look here. This data has some weird distribution, isn't it? We want it to look like this. What can we do? During the training process, we can say, guys, PZ of X, we just want you to look like a bell curve. We want you to look like Z given X, because bell curve would have looked like this, isn't it? And so what do we want to do? Go back to your loss function. And so, guys, I'm giving you as intuitive a discussion as possible without bringing in scary beasts like the elbow, right? So the loss function, actually, I'll bring it in, but you may not recognize it. So the loss function, do you remember, was in the case of regression, like pictures, it was basically, you give it an input X, it becomes Z. And then what do you want to do? You want to reconstruct. You want to reconstruct X given Z, right? And so what you want to do, the first loss term is, you want to maximize you want to, okay, let me not put it this way. Because that would be the elbow term. Let me just put it this way. X prime minus X square, you want to do this, right? Minimize this. Simply. This is your reconstruction loss. Right? For reasons that I won't get into, the full formalism uses log P X given Z and so on and so forth. But why we do that, forget about it. So guys, this part is familiar, isn't it, guys? This is your reconstruction loss. So you say you need to minimize it. So that is a given. You can't avoid that in an autoencoder. A good autoencoder needs to do that. But you add one more penalty term. You say, and the divergence from a bell curve should be minimal. Do you see that? In other words, the divergence from a bell curve should be, now let me hope that I don't get my P's and Q's reversed. I think I might actually, because I'm not looking at my notes. So I hope I don't get it reversed. X given Z, Q, X given Z. But basically, minimize the divergence between the bell curve and the distribution that this is leading to. What is it leading to? The data comes in, it becomes Z. Minimize that. Make the distribution, in other words, make this guy look like this guy. And if you don't, if you just go spread it out, there is a huge KL divergence penalty. And you need to reckon with that. Are you seeing it? So now, as the neural network learns, the encoder, decoder, gradient descents, backpropagation, all of that happens. It has two competing loss functions to do. If it just has to satisfy the KL divergence part, it could have said, forget about the input. I can just make a nice bell hill in the center. Isn't it? A normal distribution in the center.
You are constraining the machine to converge it.
Yeah. To the center. But at the same time, respecting the separation.
Yeah. That's what
Respecting the separation of the, for example, the digits or something like that. Isn't it? So there are two competing forces. One force, the reconstruction term, encourages us to keep them separate. And the KL divergence term, bring it together. So at the end of it, what will happen is, look at this situation. Do you see a good compromise? The yellows are together. They are separated from the purples, are separated from the blues, but all of them put together look like a bell curve.
Yeah.
The center. So these are two opposite forces. And one of the things you can do is when you put this term, what people can do is they can actually put a parameter here, a degree parameter. Let's say that this is, so suppose you want to take, so suppose I take A and B. You want to say, I want to give, let's say 30% importance to A and 70% importance to B. Let's say, what will you do? You'll say 3 plus 0.7 B. You would do that, right? So, or it is the same as, which is the same as 1 minus 0.3 B, isn't it? So what you can do is, you can have a parameter, let me call the parameter beta, for the reconstruction loss term, plus 1 minus beta, the other term, right? The KL divergence term. By that, we are controlling how much importance to give to each. If you kill the KL divergence term, you'll get your ordinary vanilla autoencoder. If you overemphasize the KL divergence, what happens then? It becomes a nice round hill in the center, but you can't tell the separation would be lost, right? And so there are opposite forces that are at play here, right? So that is the more sort of a full definition of the variational autoencoder. But the beauty of the autoencoder, and that is worth emphasizing, is that it leads to the first really successful generative AI model, right? Because as you can see, that it was the KL divergence was sort of the one missing term that was needed to make this into a space from which you could confidently, latent space from which you can confidently sample a point and be assured that it will look realistic when it gets decoded. Isn't it? It would look realistic when it gets decoded. And thus a generative model. Now, this generative model has a few variations and problems. One problem is people say, well, you know, KL divergence. Then came a guy called Wasserstein, right? A mathematician named Wasserstein. He said, I have a better idea. KL divergence is not really a distance. I have a better notion of a distance. And what is that notion of a distance? It's the Wasserstein distance. And why is it called Wasserstein distance? Well, because in honor of it's eponymous to the mathematician. Wasserstein distance says that if you remember that we had these two things, right? This distribution, and what was the other distribution that we drew? This. So think of it this way. One intuition of a probability distribution is that I find very useful is that take 1 unit bucket of sand. Are we together? Take 1 unit bucket of sand and just pour it. And by the way, if you ask me, how do I think of probability distribution? Frankly, I think of it like that. I like to have very intuitive pictures in my mind. So the moment I see probability distribution, I immediately think of my kids playing on the beach with buckets of sand, right? So you have to pour the bucket of sand along the x-axis, along this axis. right? Or in a multi-dimensional space along a certain plane or hyperplane. So you realize you have one unit. So if you pour more sand here, you have to put less sand there. You won't be left with that, right? Because the total amount of sand, the total amount of sand in both these cases is just one bucket, right? Whether you take the yellow line or you take the blue line, it's a purple line, it's still the same, one unit. But then I can ask a fun question, which is that suppose I was sitting at the yellow sand hill.
So that's what it's like the same bucket.
Yeah, same unit bucket. So here's the thing. You first made the yellow heap. And now I ask you this. No. I don't like this. I want the purple heap. Right? So what do you need to do? You need to scoop some sand from here and move it to from the yellow heap and put it in the purple heap. Does that make sense? No. So the question is, what is the minimum? If you're intelligent, you'll find a good way to move the least amount of sand, right? Efficient amount of sand. So would you agree that the amount of sand that you have to move to make the yellow hill into the purple hill is a measure of how much they differ or how far apart they are? Does that make sense? Do you see the intuition? Very simple intuition. The amount of sand that you will have to scoop up from the yellow and move around to make the yellow heap become the purple heap is a measure of how far apart those two heaps were, both in shape and in distance from each other, isn't it? And that, for very intuitive reasons, instead of remembering it as Wasserstein distance, so when people say, when you use formal language, say Wasserstein distance, but in your mind, tell yourself, Earth mover distance. Right? The difference between these two hills is effectively how much earth or how much sand, I think of it as sand, that you have to move to make the yellow hill into the purple hill, right? And now those hills are probability distributions. In fact, that is the only intuitive picture I carry in my mind of a probability distribution. It is how you have spread, or a problem has spread, or situation has spread a unit bucket of sand, right, in the latent space. So now, what uses this intuition? Well, we wanted to make this distribution look like this distribution. I can certainly think of it. I can put a loss function that derives from Wasserstein distance, earth mover distance, rather than KL divergence, isn't it? That will work well. In fact, that has a virtue. Earth mover distance is symmetric, right? So the amount of effort that you have to do to make the yellow heap into the purple heap would be the same amount of effort you'll have to do to restore the yellow heap from the purple heap. Would you agree? Same amount of material has to move back and forth, isn't it? So in other words, the distance between the Wasserstein distance between purple, the yellow and purple is the same as the Wasserstein distance between the purple to yellow heap, right?
Yeah.
Does that make sense? Which is an added benefit because it is truly a distance, not just a divergence. And in the variational autoencoders, some of the more recent versions preferred the Wasserstein distance. Then now you may say, why didn't I start with a simple intuition? Why did I have to bring all that Bayesian inference reasoning and KL divergence?
So to visualize, like, take the example of national inst exam, the data. This is one point of purple is one set of data points and yellow is another set of data point. I'm not able to connect. We are comparing anything to see whether
No, it's a probability distribution. These are not data points. This is the probability of points landing in the latent space. So this is your Z space. In the latent space, right? This is the probability distribution.
Okay.
Right? Probability distribution. So guys, these are two ways that you can do that. Now, There is a problem though with variational autoencoders. Guys, can I take another half an hour today? We want to do. Are you so far with me? Like, are you understanding all this? Today was a little bit long intellectual journey, but the fruits of it are amazing. Generative AI. So how many of you want to learn generative AI?
Everybody.
Everybody, right? Well, that's what we are learning. We are learning generative AI. Literally, the foundations of generative AI. This is it. Are we together? Now,
So just one question, in this versatile distance, if you are moving things,
Yeah.
the, the sand or whatever it is, the distribution. Final state will be used at the separation will be there more, right? Because we are trying to map.
yeah, that's right. So the Wasserstein distance concept is coming straight from math. It basically says that if you look at it as two heaps, how much do you have to move sand or earth to convert one heap into the other? These are probability heaps.
So both are effective, right, in a way? If you move sand from this guy to that guy, this guy becomes changes, and this guy also.
This guy disappears, the only other guy. You're saying convert the yellow into the purple.
Okay.
Keep moving sand around and convert the yellow into the purple. So yellow is no more, purple is there. To and from, right? So how do you do it? You see kids playing in the sand, right? They'll have a heap of sand. Then with their hand, they'll just keep molding and moving, and they'll make castles. And you literally see them do that. Yeah. Whenever you see them do that, next time you're on the beach, think Wasserstein distance and variational autoencoders in action.
Stable diffusion.
And stable diffusion, yes. Right?
So Yasif,
You're seeing it happen.
one question, why is that considered as a foundation for generative AI? Are we trying to fit the distribution into some one way to other way? Is that the foundation for?
No. See, I'm telling you one of the most powerful generative AI models. Today, I introduce you to the first one.
I understand, but I still don't get why this is considered as sort of even the simple generative AI. I'm still trying to get that.
It is generative. Why?
Why?
Good question. Let me repeat that. See, what happens is that if you can force that all inputs X will get mapped into this space, right? The encoder network, the FX encoder network will project X into this latent space, Z space, belonging to RD, to some point here, very close, in this very dense region. Do you see that this region is very dense?
Yeah.
Right? And then what happens? This machine has learned, what has this machine learned? That if I decode it, let's say, let me,
Okay.
you'll see. Let me go here. So now, if I sample any point from this, let me sample it with a different color. I randomly pick this point. Do you see me pick this point, Z? Some point Z. And I pass it through a decoder.
Okay.
What can I be sure of? It will look like points around it, right? They are realistic points around it, isn't it?
Yeah. Yeah.
In fact, it will have interpolated features
Okay.
of the points around it. And therefore, now, how many points exist in that dense region? Krishna? How many points exist in that dense region?
I mean, I don't know. It's
Infinitely many points, right? Geometrically. See, you trained it on a finite data set. Let's say that you trained it on 10K or 100K data set. Yeah. It doesn't matter. What it has discovered is a dense region,
Yeah.
right, where these points live. It has found the neighborhood.
Okay. So decoder can potentially, expand it. In other words, generate it, right? That's what.
Yeah. No. Decoder is another network, right? Its purpose is X prime is equal to decoding of Z.
Yeah.
Right?
Yeah.
It will decode any Z, not only the Z that belongs to the real data, because you can randomly pick any point that doesn't exist in the training data. Any point.
Okay.
And you know that confidently that it will decode it into something realistic.
Okay.
That's the point. And
Got
that is, it's a very simple statement I'm making,
Yeah.
right? That because this region is dense, any point that I pick in this space
Yeah.
will be realistic.
Yeah. I think I got it. Thank you.
Got it. And you realize the far-reaching implications of that. The far-reaching implications of that is you just have cooked up a very effective generative model. So when this variational autoencoders came, and it is now almost going to be a decade, not quite a decade, but yeah, almost a decade or so, suddenly we found that people started creating faces that didn't exist, right? Now, this is only one of them. The other class of algorithm I'll teach you next time, GANs, and then there's another, and then there's another, and the rest of our course, and then the boot camp after that is all generative thereafter. Generative in AI has always been hard. Discriminative has been relatively easier. Right? To come up with a good generative model is not that easy. And here we are looking at a very effective generative model. Right? There are entire websites. They don't specifically use this algorithm, but if you just want to play around, one of you, if you go, or maybe I can show you just to get you a sense of how these things work. Now, again, I must say that it does not specifically use what I have just taught you, this algorithm, but in the same family of generative algorithm, there is this person does not exist.com. How many of you can tell that this is coming from a generative model? It's not real. There is no such person. Do you see how impressive it is? People often talk about the unreasonable effectiveness of mathematics.
Hard to believe.
Yeah. And so do you realize that it is coming from the simple mathematical ideas that I just taught you? Isn't it worth going and reviewing those ideas? Right? I hope it does. Well, let's refresh this page. Oh, refresh it again. Look at this. Look at this. Look at this. Can you say that these are not realistic? Right?
What if it could generate somebody really like this?
Yeah, I mean, it does look like some real people. By the way, this one doesn't use a VAE. It uses something called GAN, style GAN. It is one of the things, that's the topic of our next week, GANs, generative adversarial networks. And you will encounter this. But I'm giving you the power of generative. This is a small change. We encountered the first generative model. Now, guys, do you see the power of all of these ideas?
So what if the generator accidentally like my face while I'm here?
Yeah. Come again?
What if it generates accidentally my face?
That's good. Then you hopefully a better version of your face. Then you can put it on LinkedIn.
Yeah, Facebook is
A
introducing
lot
the
of people do
digital.
that actually.
Yeah.
They keep playing with it till it looks something like them, but a better version, and then take it, crop it, and then put it on their LinkedIn.
Is it coincidence that it's all white people?
No, it's because the data has been trained accordingly. But if you play around with it more, it will actually change. Right? It's not always so, but yeah, it's not coincidence. It's because of the nature of the data that it has been trained on. You train it on a different data. And by the way, this website does it like that. There are different websites that are more ethnic, right? Or they're racially more diverse, right? And there are websites that only produce Indian faces and so on and so forth, Asian faces and so forth. So there are all of these. It's very easy. Actually, why don't you take that as a homework? Build one. It's really not that hard.
It is intended
Wow.
to create images which is not like a real person, or it is just a process.
No, there is no intention. It is just sampling off. That's it. It is just sampling off a latent space. See, you have a machine that can sample off a latent space, and you know that you have trained a neural network to generate a realistic face out of it. It's completely random.
So let's say based on the race, one race, the people look like, so.
You can do that.
Try with that.
Yeah.
Based on that will bring up a possible.
No, see, this is a simple website. They wanted to keep it simple, but you can actually do a slide. You can actually slide. See, remember, you can do, guys, listen to me. You can do vector arithmetic in the latent space. Suppose you know that in this region of the vector space, all the faces are children. And in this area, it is all old people. What can you do? You can age by sliding from here to there. You can have this place mostly, let's say, of Caucasians, and this place mostly of, let's say, Tamil, right? And now you can figure out what exactly would be the offspring of people if they're married.
So Asif, is it similar to deepfake?
It is deepfake. It is deep. Why is it called deepfake? Well, the fake means it's not real, and deep because you use a deep neural network. Autoencoders are deep neural networks.
Asif, Meta just announced recently that they're going to start marking AI versus real. So I think they're coming up with the digital watermark for AI generated.
Yeah, that is true, and everybody is, because Europe AI Act is requiring it actually, that you must digital watermark generated
This
content.
one has a watermark.
Yeah, it is a style GAN. Yeah, that is true. But see, it doesn't have, I mean, yeah, it does have a thing there, but you can crop it and remove it. But what the new watermark that people are saying is something you cannot remove from an image. Embedded sort of a signature that you can't remove. That you can't just simply crop it and say, this is it. Right? And now I'll say, if you are clever, you can actually find, if you're really good at it, you can actually find subtle signals that will tell you, not all the time, but sometimes, that this image is unrealistic, right? Or that it is a fake. But it takes an expert to do that. I'll let you, as a homework, figure out what are the rules that give you a clue whether some image is realistic or not. But most people can't do that. It's very, very real. So guys, with that, I would like you to humor me with one more algorithm, which you can consider as optional, but I will mention because it's at the heart of, one of the most successful things that happened was DALL-E. You remember? In which you could say a carrot taking a dog for a walk, or a daikon taking a dog for a walk. And then you would literally see a daikon walking with a dog next to it. Imagine, you can create absolutely impossible situations. So today, what do? You say cow, the cow, astronaut on a cow on the moon, or astronaut on a horse on the moon, and all sorts of images come by, or weird things, right? So, or for example, you winning the Nobel Prize in the Nobel Prize ceremony, and it will create a realistic picture of you in the Nobel ceremony winning the prize, being handed the prize, right? Or something like that. Just about anything you want, it can do. But see, the whole history of this is, it started with an algorithm, which I'm going to take you, which is another variation of the what? Autoencoder, variational autoencoder. So there is a problem here with variational autoencoder that people realized. And guys, what I'm going to talk about is a slightly advanced topic. The only reason I'm mentioning it is because these things are of very current significance. Algorithms, the first version of DALL-E was based on these ideas. Now things have evolved. The newer versions are based on a slightly different idea, and those ideas you'll encounter in your boot camp or subsequently, diffusion models and so forth, but not in this course. This course, we are already going, are we going slow or fast? Yeah, we are going already quite fast, so we won't do that. But let me explain. It's called VQVAE. The VAE stands for Variational Autoencoder, but VQ stands for Vector Quantized. Now, what in the world is this? Is one of the most powerful autoencoders out there. There is a problem. It's called posterior collapse. Posterior collapse is a very interesting problem. What happens is, it manifests itself in this way. No matter what input you give, it starts producing, in the worst case, whatever so you have this autoencoder, variational autoencoder. Let's say that, for example, you're giving it digits, some digits, it figures out how to minimize the loss on it, right? So 9. You give it a 2, but it produces something that looks like a 9. Right? As an example. Or it keeps on producing an 8 repeatedly. And it happens because it has figured out how to produce some good shapes that are realistic. Are we together? And it goes on producing it. So no matter what your X is, and therefore no matter what your Z is, it will randomly, the decoder keeps producing realistic images, but which are very boring, dull, and like basically not what you expect it to be. And it lacks variety. It gets locked in. There are reasons for it. And the reason is that it is basically not, so you have a probably, sorry, what did I just do? Oh, this touch, I have to disable touch, okay. So instead of respecting this, or rather this function, fx, z is equal to fx, it just ignores it. It just takes a point and then it has its own way of gz producing something realistic, right? So irrespective of what the encoder produces, it will ignore the encoder and it will decode something of its own. Are we together? It happens sometimes if you make the decoder too powerful, there are reasons for it. I won't go into all the technical reasons. If you make the decoder too powerful, it just starts memorizing some realistic shapes and regurgitating them. Or it happens because you put too much, like your balance between the reconstruction term and the KL divergence term is not well done, right? So it's mixing it all up. So it starts doing things like that. There are some reasons for it, technical reasons. We won't go to it. So variational autoencoders have been going through evolution. So one day, one of the papers that came out that was very influential, and actually a variant of this was the foundation of DALI, DVAE, which is basically a vector quantized variational autoencoder, but slightly different, like not so hard quantized, soft quantized. But I will talk about vector quantized variational autoencoder, what it does. It says this: suppose the encoder does this business. And pay attention, and if you don't get it, it's all right. Huh? Suppose you give it n, x, which belongs to a high dimension space, Rn. What you do is, you say, let's see, think of a CNN. What do you do from the CNN? You create lots of feature maps, channels, right? Let us say that you created, for the sake of argument, I'll say 100 channels, 100 feature maps, right? And I ask you this thing, that each of the feature maps, you make it into a vector. So somehow f of x produced a vector z1, right? Z1 all the way to z100, right? It produced these vectors, like feature maps, which you can convert to vectors, linearize, whatever it is. You do that, these vectors. Now, here's the interesting thing it says. It says, you know what? I don't want to send this to the decoder because, decoder can misbehave. What I will instead do is, for each of the z that it produces, why is this not scrolling down? 1 second, right? Okay, so I'm having this problem, which I keep having with this OneNote. Every once in a while, I have to restart it. So, and guys, we're almost done. Huh? I know that some of you are beginning to pack up. Oh, all right. So what you do is, you maintain a code book. This word is important, a code book. Right? You maintain a library of vectors. Say, you maintain k vectors. Library of k vectors. So k is equal to 512 vectors, right? This is your code book. Think of them as k pictures or faces. And you ask for each of the zi that gets produced from z1 to 100, you ask which vector it is closest to. So let's say that you name the vector A, B, C, D to whatever. Well, English doesn't go to 512, but whatever it is, right? What you do is you find the closest, so let me just call this the closest embedding vector that is the codebook vector. Let me just call it the codebook vector, the closest codebook vector that it is closest to. And you replace Zi. So let's say that Zi is closest to Q. Right? In other words, Zi square is smallest. Euclidean distance of Zi to the Q vector is smallest. Am I making sense? And Z will of course belong to a d-dimensional latent space. That is all right. And so this Q vectors also belong to each of the K vectors in the code book. The library also belong to d-dimensional latent space. Now, what it basically means is, I'll give you the intuition. Let us say that you have the actual code book. Actually, what should I use for code book? Okay, let me use the word E. I think that's what the research paper uses. E1, E2, E3, E4, E5. Let me just take these few. Right? Now, let's say that Zi landed here. Z vector, some Zi landed here. Which one is it closest to?
E1.
E1, right? This is the one. So what you do is you replace this, you maintain a table and you say, so 10 by 10 table. Why? Because I have 100 of those, right? So you say, all right, or you could just make it a linear one for audio, but because for vision you use, remember we are used to CNN grids. So let's just take 10 by 10. What you do is here, I just need to remember that this is 1. Why? From the code book is the first vector. I don't even need to remember the vector. I just put 1 here. Then I get another, so another feature map I take, and then I realize that, oh goodness, that one landed, let's say that one landed here, right? So this guy, let me call this one Z2, landed here. So what is the, oh no, well, this is 2. So let me just not put it here. Let me say it landed here. So what is the closest neighbor? 4. So I'll go put 4 here, right? So what can I do? If I have 100 vectors representing 1 input, I can fill up this 10 by 10 table, isn't it? Now you say, oh boy, you quantized it. In other words, you are picking only amongst these. Don't you think you'll have a limited variety? Because if you're not going to feed the original, which could be anywhere in the infinite space, right? Z's could have been anywhere in this infinite space because it's a dense space. You have replaced a dense space with a very finite, not just sparse, very finite set of only 512 possible positions, isn't it? Vectors.
So I was wondering how does it differ from the sparse autoencoder?
No, very different. Sparse is
So
about
here you are saying quite well.
Yeah, pick. So suppose this library, imagine that this library had just 5, just for example, take only 5 items. Your library had only 5 items. Your code page, the code base, code book had only 5 vectors, 5 items. So then just like this picture. So what will happen? Every of the Zi you would replace with one of the 5 values. That is massively quantizing it. You're not saying you find the nearest neighbor. You're not even giving it a choice of being anywhere. You are saying pick a location, one of these 5. Which one are you closest to? You may say, oh my boy, this is pretty bad. How will I have the variety in decoding it? Won't I? Will it not limit the space of things that I decode to? Isn't it? So now let's think through it. Suppose I have this code book. So by the way, I use 10 by 10, right? In the example they take is 32 by 32. But because in the research paper they took 32 by 32. So you realize each of these cells, how many possibilities are there? The value in each cell, how many possibilities are there? Any one of them could have been the neighbor, right? Right. So in this particular case, suppose k is 5. I have a k possibilities, isn't it? K possibilities. And the grid size is 32 times 32. That happens to be give or take 1,000, right? 1,000. Even if you take just 5 items, do you know what 5 to the power 1,000 is? Right? It is it's a pretty large number. But when you take 512 to the power 1,000, right, which is basically, let me be very, very precise here, 32 cross 32, right, because we are using 32 by 32. This number, when you realize, then your fear is gone. You know that it can capture a very, very complex reality, because this is a vast set of possibilities. 512 to the power, 512 square itself is large enough, isn't it? It's what, 250,000, right? And one squaring has already taken you to 250,000. You can think what a 1,000th power would be, right? So you have a very rich variety, and so you don't have to worry. What you do is you create this code page and then you pass it into the decoder, and the decoder will do the decoding. One of the big advantages of this is you can't have mode collapse, like posterior collapse. You don't have that. This problem doesn't have. Now I've missed out a lot of features and details because I was trying to finish all of autoencoders in one session. The variational autoencoders in one session. So this is vector quantization. But the beautiful thing with this is, because we are dealing with a code page of well-behaved vectors, right? It leads to a lot of possibilities. Now you might wonder, I'll just end with the last 8 minutes with, okay, you say, how in the world can you train a neural network to do this?
Or is it how the K
vectors? Who decides the K vectors? How do you discover them? And what's the answer to that? Let backpropagation discover it. You say that, well, that seems like backpropagation seems to be the magical way to do everything, right? So what you do is, for K vectors, so take, let's say 512, and let's say that you take 64 dimensional vectors, or whatever dimension, I don't know, pick your dimensionality, right? So what you do is, you take 512 random vectors, right? So your E1 to EK, each belonging to whatever the dimensionality is, just randomly initialize it. But you need to, the magic comes through the loss term, isn't it? So now let's write a loss term smartly. And actually, when you see what I'm doing, it is dead obvious. And this is the beautiful equation in the research paper. So you have the reconstruction loss, right? The usual reconstruction loss. So can I just leave it as reconstruction loss, x prime minus x square, etc., right? I won't write it, reconstruction loss. Then what you do is, you say that, see, you want your Z's, the encoder, to land its objects close to the, if the code pages are beautifully done, let's say that you have the most magical vectors discovered, a code book of most magical vectors discovered, then every Z should land very close to at least one vector in the code book, isn't it? That is it. So therefore, if it doesn't, then you need to add a penalty term to that. So there will be one penalty term, which will be E, the nearest I minus Z, right? Some code page, some vector E minus Z, and this distance square, you want to minimize it. There's only one little caveat that this thing mentions. When you backpropagate, when you do this loss, what you want to do is, you want to change the autoencoder such that Z moves towards the code vectors. But at that moment, for this term, you don't want to be moving the vectors themselves. You're assuming that the vectors are perfect. So the trick you use is you say that you freeze the gradients. They use the term SG in the paper, but anyway, it doesn't matter. It just means that hold the code book fixed and try to align the Z to the code book. Right? That is one. And then add another term which does the opposite, because how do you know what the good code book is? In the second part, you assume that the code book, another term, changes the code book so that it better aligns to what it believes that the encoder is doing its job correctly. All right, it's producing good Z's. So you want to move all your code books around, code book vectors around, so that they get closer to the actually encoder produced Z's, latents, isn't it? Do you see that, guys?
Is it like, it's like moving the line correctly to fit the data?
Yeah, exactly. Sort of like that. So there are two different. So what happens is that you do two things in parallel. First is step by step. First you say, okay, encoder is good. Let it produce the encoder wherever it is. So encoder, decoder, we can obviously, this is your vanilla loss, reconstruction loss. So ignore that. You have a problem. You need to discover the best code book and the best encoder. Decoder will get trained from the reconstruction loss. Don't worry about it. But encoder needs to be trained and the code book needs to become good. So you do it by alternating, having a loss term for one and the loss term for the other. Right? One loss term says that encoder is doing a good job, but I need to change the code book, improve the code book, the vectors in my code book. So you have a loss term for that. And then the other term says, hey, given the code book being correct, assuming the code book is correct, let me improve the encoder, align the encoder to produce Z's close to the code book. Isn't it? And so this is the important. Do you realize, guys, by now you must have realized we have taken a long intellectual journey. Everything, do you realize, comes to creating a smart loss function. Right? And then the rest of it, back propagation, gradient descent, etc., takes over. In fact, neural architecture, the magic of it is dreaming up a neural architecture, dreaming up a good loss function. That's the game you play in this field.
So the code book is constructed by.
You learn it.
No, code book.
Code book itself.
It's manual. So because I'm not learning.
No, you are learning it. No? See, what happens is you take a pile of data, lots of data though, right? And then you take a neural network, encoder, decoder, right? With a code book, In the beginning, encoder sucks.
No,
And,
the code book is.
No, you initialize it with random vectors.
Oh, code book is also random.
Random. That is the point I'm making. So in the beginning, what will happen? Code book will be made up of totally junk vectors, and encoder will be producing junk latent.
Okay, then your
and the decoder will be decoding junk. And the whole process is, this process will make sure that it begins to behave like a proper or encoded autoencoder. This term, second term, will make sure that the encoder tries to produce things close to the code book, assuming that the code book is good. Now, you know, in the beginning, even the code book is junk. But the last term is doing what? It says that assuming that the encoder is doing good, let's improve the code book. So both the encoder, decoder, and the code book, all three keep on improving. Like basically, I've created a loss function that forces all three to align under the guidance of the data. The data in the loss function, right? That is the beauty of this thing. And what you just created is vector quantized, variational autoencoder.
I say both of those, the second two parts both have to be added together. Is that correct?
Yeah, right. Oh, by the way, guys, in this notation, right, I have forgotten a lot of the sigmas, and like I'm giving you the logical picture, the terms picture. So forgive my mathematical sloppiness. The problem is if you are mathematically too precise, then it becomes hard to understand, right? So this is it. So guys, with that, we end variational autoencoders. I'll put lots of Jupyter notebooks and links and so forth. Run those notebooks, guys, play with it. Do you realize that what I just explained to you in the last 3 hours can produce magically very, very realistic things. In fact, if you got this variational autoencoder, you have understood the hardest part of things like the hardest part of most of it, of things like stable diffusion. We still have to introduce the diffusion part, but you have understood at least a big chunk of it. You have understood how the original version of DALI worked and so on and so forth.
So, Asif, is it just for images or even for text?
No, for everything, audio,
At
text,
the end of the day, it's a vector, so it's a
Okay,
number.
fine.
So we can put it.
anything you want.
I say if you could go to that last function. Yeah, so here, as part of once we calculate the loss for every cycle.
Yeah.
For the first, after in the penalty, the first one where we keep the E as a standard gradient constant and then we move it. So as part of every feedback loop on the back propagation, it calculates and tries to find out.
Yes, great. So the fact that you can differentiate, see, when you take the gradients, right, to improve the encoder, when you take the gradient and update the encoder, you assume that E is fixed. You don't try to shake up E. You only look at the loss with respect to this, right? And when you are fixing the code book, you just assume that the encoder is fine, and this term applies to improving the code book.
And this goes for
every cycle. Yes, isn't it amazing? Like, see, this back propagation is just amazing. Imagine a whole wave of water coming through. It's the metaphor that I have is it's like you have one field here, one field here, one field here. One is growing something, one is growing something else. But when the back propagation wave comes, they all get nourished.
So that way the code book also gets refined.
Yes, code book also gets refined. Oh. Everything, encoder gets refined, decoder gets refined, code book gets refined.
Okay.
Beautiful, isn't it?
Yeah. So from an analogy when we went for the feed forward network where we were dialing the weights and the biases, here we are dialing
these parameters, the vector parameters. At the end of it, see, encoder, decoder are just weights and biases.
Correct.
But code book is just vectors, which is just also parameters. At the end of it, they're just some random values. Even those values we are improving to backprop. Right? As far as the machine is concerned, those are also just parameters, and they can also be improved through backpropagation.
So the difference between the vector quantized and the one before is that it's basically like we are limiting the
space of values of Z. It can take only one of the discrete values. That therefore the word quantized. The vectors are quantized. The Z's are quantized to one of the 512 values. That's what it is.
So, Asif, like I have a quick question. Sorry if I'm asking a basic question here.
No.
I start with the assumption that code books are well-known quantities that you have referenced for your model. Now
you learn it from the data. You co-learn the code book and train the encoder, the rest of the encoder. And code books are part of the variational autoencoder. Given a particular data set that you train it on, it will develop the perfect code book for that data set.
Oh, wow. Okay.
Just amazing, guys. You know, the sheer intellectual elegance of these ideas is just amazing. So, you know, when we talk about all this generative AI, people go like, oh, look, in 4 lines of Python, I did that. Yeah, that is amazing. But not many people delve into the foundational ideas that make it possible. It's just amazingly beautiful ideas and very simple ideas. You know, we're not talking about some quantum field theory here. We are talking about some very basic probability theory, very Bayesian probability. We are talking about vector calculus. That's all.
So I have 2 questions. Okay, the question number 1 is when we started this class, okay, you mentioned about particularly for the variance inference, we are inferring things.
Yeah.
Okay, how we can connect that with the
this entire process helps you infer something hidden. What is hidden? The code book and the Z, the latent state that it produces. That's your latent, right? Remember, what was the journey? Observable is the data input and output. What is the latent? The Z. And also Right?
So that is we are inferring based on the outcome.
Yeah, that is right. Yeah. So
This is considered self-supervised or unsupervised.
yeah, these are all self-supervised learning algorithms. Autoencoders are self-supervised. Right? People also use the word people use all sorts of junk word. See, guys, at this moment, the things become fluid. Some people call it unsupervised. Some people will call it supervised because it has the nature of both. Some will call it self-supervised. I think self-supervised is the term that most people are gravitating to. And then I've also heard weird terms like auto-supervised or whatnot.
Autonomous supervised.
Yes.
Hey, Asif.
Yeah.
For the last like 30-45 minutes, I lost you. I couldn't, because a lot of information I couldn't digest. So, is there a way we can review the last 45
Yes,
minutes?
guys, one thing, very good question actually, Prashant. Can I answer this, guys? I must say one thing. If you go to the course portal, and I will add the video, I gave a research paper reading on vector quantized VA, the last thing that I covered. If you go to the research paper reading, and all of you are members of the weekly seminar research paper reading, literally the very first research paper reading that I added to the portal was vector quantized VA. Do you see this, guys? Right. This was a talk I gave a long time ago, and I have created out of it a quiz, the summaries of it, and so on and so forth. So there's a lot of collateral, educational collateral that came out of my weekly paper reading on vector quantized VAE.
So this is on the
Course
paper.
portal. Yeah, weekly seminar. If you go to the weekly seminar, so guys, there I've devoted more than an hour just to. How long is this video? Let's find out. It is. It landed in the almost 1.5 hours, 80-minute video that is just on VQVA.
Also, that code page that you're talking about are start with random values,
Right.
Slowly align to
Yes.
the
It
closest
learns.
to your value,
Right.
to your X value.
Yeah. It basically discovers what are the best code book you can create.
Got it.
Code book of vectors or arsenal, a library of vectors you can create.
And so this one is stable diffusion based on this, or?
Yes, it's literally based on these ideas. But wait for that. We'll come to all of that.
That is why you can move a mustache over and stuff like that.
Oh, that you can do even with this. You don't have to go to diffusion. By the time you come here, now you can do everything. Yeah. With variational autoencoders, you can do all of that.
And so since this is a quantized model, it can fit on a laptop and stuff like that.
Oh, no. It's not quantized from the practical perspective. It just means that the Z space, the latent space is quantized. That's all it means. Okay, guys, those of you who are remote, any questions? By the way, guys, was it useful? Like, did you feel you understood at least some part of it?
Yeah, very much.
Please do review this. It is really one of the breakthroughs. Variational autoencoders are not a minor thing. They're one of the beautiful architectures. Autoencoders in general and variational autoencoders family in particular. These are transformative.
So is this math? Sorry.
Asif, one question. Is
Go
there
ahead.
a decoder version for this, or we're not going to be looking at that?
No, there is an encoder decoder. No? Autoencoder always has an encoder decoder. Remember that the first term is going to train the decoder also.
Got it. Okay. Thank you.
Any other questions, guys? Any other questions?
So all this math is developed recently, or this YAML, or this math was already being.
Oh, vector calculus and probability theory has been there since the dinosaurs roamed the earth.
Right. So what was the use case for those things? Because we are using
Mathematicians don't think use cases. They develop mathematical theory for the sheer beauty of it.
But it's very abstract, right? In that case, because I'm just looking at I see that it's a distribution and I'm getting some function.
Yeah.
I'm always saying that I have all of my time, so I see that how I can sort of
exactly
connect those.
See, that's why mathematics is always right. While others work, mathematicians play. Right? That's a common saying that the best of research and the best of science is done when researchers don't work, they play.
I
So
you're still